Okay class, let's continue the discussion. The following video clips are for the missing class on February 2nd. So February 2nd, our ECE 3101, Signals and Systems. And we'll continue our discussion. Last time we stopped at discussing the convolutional integral, which is introduced to calculate the zero-step response of a linear time invariant system. And as I mentioned, the most important part that you will need to remember will be this guy. Okay. This is the formula we currently use to calculate the zero-state response of a linear time invariant system. And we'll start our discussion today from here. So, zero-state response. Y of t, this is of LTI system. The zero-state response, as we discussed, can be obtained using the convolutional integral, where f of t is your input, h of t is the unit impulse response, mathematically this is equal to the integral. The integral is obtained like this. So y of t is actually the response at time t, right? It requires several things, or it's actually the result of the following. Now, it's a result of the input signal f, but input signal f spans from t equal to negative infinity to t equal to plus infinity. Every single point on the input signal can affect the output at time t. So you have to look at the entire time axis, so negative infinity to plus infinity. Since t is already used here, we cannot use t anymore, we use tau. So this will be the input signal at time tau. So this guy is your input at time tau. And we're going to look at tau equal to negative infinity to plus infinity, meaning we'll cover the input signal at each single time instant. Now, f of tau is the input that appears at time tau. It will generate or results in an impulse response. So a single point of your input will generate a unit impulse response, because unit impulse response is the result of also the signal at the singular point. So we'll generate an h. The magnitude of h will be determined by the value of the signal f of tau at this particular time moment. And since we want to know what happens at time t, that's already after this impulse signal has evolved sometimes. Since it starts at time tau and the ultimate goal is t, the total time has elapsed from tau to t will be t minus tau. And then we'll add everything together from negative infinity to plus infinity. And to understand this, you can look at the following example. For instance, an input is supplied at the 1 minute mark, tau equal to 1 minute mark, and you want to know what happens at the 5 minute mark. And of course, the total time has elapsed will be 5 minus 1 equal to 4. This is how everything will add up together. The output at time t, how you still feel after a certain amount of time, will be, then you will examine all the inputs at each time instant, the response these inputs are generating, and then of course each single point you only look at how much time has elapsed from the instant that the input is applied, and you only worry about, well, at this particular time moment, what happens? How do you feel after so many minutes as well? This is how we interpret this convolution integral. And as far as this course is concerned, our requirement about convolution integral is that you can use it to calculate the zero input response to a linear time invariance system similar to this particular example. Meaning you will have to be able to use the table to do the calculation. So the input signal will take, already takes a form that you can see from the table. Now of course everything can be done through hardcore math, but that's a relatively more complicated job to do. For instance, we'll start this by an example. Let's assume we have an LTI system which has the unit impulse response h of t equal to e negative t u of t. Okay? Now let's assume I now have an input signal f of t equal to e negative 2t ut. And my question is, what is the corresponding zero state response to this f of t above? Now, the response apparently will be the convolution integral based on our current knowledge, meaning we have to take the convolution integral between the input and the output, and the unit impulse response. So f of t star h of t. Now the table in the text for this table 2.1 on page 125 said, well, I can use line number 4 in this table, and as a result I should look at negative 2 minus negative 1 and e to the negative 2t minus e to the negative t times ut. So organizing the term, you will have e negative t minus e negative 2t times u of t. Okay? So using the table, this is how everything can be done. Now, if you don't feel like using the table, you can use your hardcore math based on the definition of the convolution integral. Meaning you have f of tau, and you're given f of t. To write f of tau, you just have to replace the time argument t with tau. Negative 2 tau u of tau. And then h of t minus tau. You're given h of t. What you need to do is to replace t with t minus tau. That will give you h of t minus tau. So we'll have e to the negative t minus tau u t minus tau dθ. Okay. Now, before we proceed to anything, there's one particular thing we can take care of first. That is, if you look at all these terms, well, this is nothing we can do. But I do know that this guy will be 0 when tau is less than 0. Right? Then the upper guy is this exponential function when tau is larger than 0. So graphically, if I'm plotting it on the tau axis currently, it should look like this. I'll use the blue. So it'll be 0, and at time 0 it will behave as the exponential curve. So this is the first, this is f of tau, right here. Now, the second term is a little strange. Now, tau is an independent variable, and t is actually a constant. We start from e to the negative t, and we use a different color. We start from e negative t ut, or in the tau axis, e negative tau u of tau. Now, what I do need to do is to figure out, well, what is e of negative t minus tau, u of t. Now, when you're doing convolution integral in this manner, a graphical illustration usually will be an easier way to do it. So we'll apply it. Now, this is e to the negative tau u of t. To obtain this guy, I need to do a number of things. First, I need to do a reversal because of the negative tau. So if I do a reversal, this will be e to the tau u of tau. See, I'm replacing all the taus with negative tau, all taus with negative tau. Here. And then if I want to move forward to obtain this guy, what do I need to do? I need to have a t there, but I need to make t tau 2 or negative tau to t minus tau. Meaning I need to make tau 2 tau minus t. Because if I replace all tau with tau minus t, what's gonna happen up there is I will have e to the negative t minus tau and u of t minus tau. This means what? This means I need to move the curve right here. So this is the tau axis. And move it to either left or right depending on the sign of t. But I'm going to move it such that this curve will end at tau equal to t. This is where we're going to have this. Right? So we start with e to the negative tau u tau. Eventually we want to see what this guy looks like, because I have to multiply this one with this f of tau, with this one. And this is what we obtain. Then putting things together, when t takes different values, when this is t, take different values, different things may happen. For instance, if t is something negative, then the other curve will look like this, and the blue multiplied by green will always equal to 0. Right? No matter where t is, as long as t is negative, there's no overlap of the two curves, so there's no way you do an intersection. That means when this happens, y of t is always 0. On the other hand, if t becomes positive, then the multiplication of the two will have some overlapped area right here between 0 and t. And outside this area, still the multiplication will be 0 because the blue curve is 0 before t equal to 0, and the green curve is equal to 0 after tau larger than t. This is the tau axis. So if you're taking the integral y of t, which originally should look like this is when t larger than 0. This will be equal to what? This will be equal to just from 0 to t. Since this is the only range, this product won't be equal to 0. Beyond this range, one of them will be 0, and that will basically cancel out the other. And within this particular range, one is e to the negative 2 tau, the other is e to the negative t minus tau. And u will always take value 1 within this range, so we don't have to worry about it. Then what you can do is to take the integral as you have done in your calculus class. Since this is with respect to tau, this negative t doesn't really matter, so I move it forward. And then we'll be taking the integration. Okay. You have e to the negative 2 tau, you have e positive tau, so we'll take advantage of both. Just e to the negative 2. Okay. And this will give us what? E to the negative 2. This will be also a negative sign. And then e to the negative 2 minus positive half plus 1. So equal to e to the negative 2 minus e negative 2t. And if we combine them together, what do we have? Y of t will be equal to two things. If t is larger than 0, we have this. If t is less than 0, we have 0. If we're doing calculus, this is what we obtain. And if we're doing the table calculation, we have completely the same thing. The only difference is you don't have to split it into two cases. This u function will take care of itself. It's like a switch. before time t equal to 0, switch it off. After t equal to 0, you switch it on, and you have this expression. So this is what we have for convolution integral. If you look at the textbook, it has a rather long discussion regarding how to calculate convolution integral. From the mathematical perspective, I will still encourage you to read those discussions, some of the examples, especially how they use the graph, sliding the one graph in to find the overlap, as what we did here. It's an interesting discussion, but from another perspective, in signals and systems, or systems and control, the most important part about convolution integral is be able to calculate zero input response when the unit impulse response takes the exponential form, and the input signal also takes a standard form, either unit step or exponential signal, as we discussed. So this is what we require you to be able to do.